Okay, now so here on screen we are going for the little bit deviation from the previous topics or the previous sessions we have seen. So that is currently we are in the topic of parabolic equations. Currently we are in the topic of parabolic equation, and now I have brought on an example related to the unsteady. I have brought on an example related to the unsteady thermal. I have brought on an example from the unsteady thermal conduction problem. I have brought an example from the unsteady thermal conduction problem. Now, my question, sir, is it related to this? Is it related to the fluids you are going to discuss about? No. Little bit deviation. I'm making it from your regular class. So that means I'm dealing with a problem where it is related with the fluid and the heat is being involved in that one. And finally, you have to tell me whether which of the problem I'm addressing in the current one. You can state it easily. You can state it very easily, but just concentrate on this one. So whereas the current problem is being considered, so that is the unsteady thermal conduction problem I'm taking it. So that is a little bit deviation from your regular fluid dynamics. So that means the fluid is not going to be dynamic in nature. So what we have considered here in this one is, so here on screen you can see, so there is a wall. There is a wall. This is being cylindrical wall. There is a cylindrical wall, as you can see on screen. I am annotating on the screen even. There is a wall, and inside the heat inside this particular wall, so there is a fluid available in between the walls. This can be the example where we are talking about unsteady thermal conduction. So what exactly the unsteady means? The flow properties, where the flow properties are varying with respect to the time. That is the unsteady in nature. And that I'm talking about the problem related to the heat transfer. I'm talking a problem related to the heat transfer only. I'll just concentrate on this word only. Heat transfer only. Now what about the mass transfer? What about the mass transfer you are taking it in this? So I'm going to deal with the problem of only conduction related in this one. As far as the heat transfer is concerned, so the heat can be transferred by the three modes of operation. So that is conduction, convection, and radiation. Conduction, convection, and the radiation. These are the three-step process, or the three process in which any one of the way the heat can be transferred. It can be by conduction, or it can be by the convection, or it can be by radiation. But as far as the researchers are concerned, they will be considering only any one of this. They'll say either you say conduction or either you say convection. But radiation is being accepted. So as far as the researchers are concerned, they will say only two steps or only two methods of possibility of the heat transfer. But as far as the regular classroom discussion is being considered, there we have to agree that it is by conduction, convection, and radiation. So not to deviate from our current one. So let us take a problem where it is being related with the unsteady thermal conduction problem. So in order to address this problem, so I have taken one geometry here in this one. So the geometry is such like, so there is a heat transfer happening in between the two walls. There is a heat transfer happening between the two walls. So let me take the two walls here on screen. So let me take the two walls here in this one. So there's a wall 1, this is a wall 1, and this is a wall 2. So wall 1 and wall 2. Right, so let me take the initial temperatures of the wall. Let me take the initial temperatures of the walls as T1 and T2. Let me take the initial temperatures of the walls as been T1 and T2. So where the fluid is available in between the two walls. Where the fluid is available in between the two walls, so let me take it as TW1 and TW2. So that is in between the wall 1 and wall 2. In between the wall 1 and the wall 2. So that is in between the wall 1 and wall TW1 and TW2 is in the wall temperatures wall 1 and wall 2. So and in between I have a complete fluid is being filled inside this particular one. So the fluid is available in between the two walls. The fluid is available in between the current problem which I am being addressing here in this one. The fluid is available in this one. Now if you concentrate on this particular problem, if you are concentrating on this particular problem, so when T1 is equal to T2 is equal to, when T1 is equal to T2 is equal to TW, so that is wall temperature. Or if T1 is equal to T2, so that means both the walls are under equilibrium. But there is something which is being available in middle of this one. So that is in between the two walls. That it is the fluid. That is the fluid. So that means when one wall is being conducted, there will be the heat need to be transferred. Heat need to be transferred from the solid boundary to the fluid boundary and fluid to the solid boundary. This is how the transfer of the heat is being happening here in this one. The transfer of heat is being happening from the solid boundary to the fluid boundary and fluid to the solid boundary. It is being happening in this one. right? So now considering this problem of walls in between the fluid. Now when we are talking about the fluid available in between the two walls, so let us take that fluid is having no velocity here in this one. Let us see if you are taking that there is no velocity change happening in this particular fluid walls, considering if there is no velocity happening, there is no velocity of the fluid, if it is not dynamic in nature, then my point of V bar should be equal to 0. Then I have taken on the conservative form of the energy equation. I have taken the conservative form of the energy equation where I have been addressed with this one. And here in this conservative form of the energy equation, here in the form of conservative equation of the energy where I have considered it here in this one. So in this form, when I am taking that there is no velocity change, that means the fluid is not being transferred. The fluid is being stagnant in that one. When the fluid is being stagnant in this one, so that means my velocity is going to be 0. My velocity is going to be 0 when I'm considering a stagnant fluid. When I'm considering a stagnant fluid here in this one, so that means my velocity is going to be 0. So when my velocity is, so that means I'm taking a static fluid. In between the two walls. I'm taking a static fluid in between the two walls. So where there is no point of taking the velocity at all. Yes. So that means my V bar is equal to 0. V bar, where actually V bar means that the x, y and z direction the flow velocity is going to be 0. So that means my velocity is 0. So when I take my velocity terms in this equation is going to be 0. So that means here I have V, where all I have V, I can cancel it. So there it is being multiplied with V. So that means this entire term will be going to 0. This entire term will be going to 0. And in this term, the V term will be going to 0. And here in this, there is no V term, yes. Wherever I catch up with the V, I can make it directly equal to 0. This is equal to 0. This is equal to 0. Here also have U velocity, right? U, V, W, all the velocities which is being addressed in this one. So that means when the fluid is not having any movement on that one, so that means my velocity terms need not to be movement. So that means the velocity is 0 velocity here in this case. So that means my simple form of the conservative equation has been changed. Just see how my conservative equation has been changed to very simplified format. So my conservative form of equation has been simplified to dou by dt of rho E is equal to, so this has been equated to 0, rho q dot plus dou by dou x of k into dou t by dou x plus dou by dou y of k into dou t by dou y plus dou by dou z of k into dou t by dou z. So this is what my resultant equation I'm left with. I have left with only this equation because in my fluid flow, in my case of fluid flow consideration where it is unsteady thermal conduction is happening, in that one there is no velocity change happening in this equation. There is no velocity change happening in this particular equation. So then my conservative form of the energy equation has been simplified a lot for this particular problem. So my equation has been resulted with this one. So that is rho dou E by dou T plus rho Q dot, right? So that is rho Q dot plus whatever we have just written, that is the equation is available here in this one. So how did we obtain this one? So that means I have assumed within a condition of where the velocity is not changing, where the velocity is not being changing in that particular case. Okay, so addressing that particular case where only the energy is being transferred. When the energy is being transferred, that is the thermal conductivity. So that is the unsteady thermal conductivity heat problem we are addressing here in this one, where the fluid is in static. So that for obtaining that particular condition, that has been resulted with this equation. Right? So this is our equation governing the unsteady thermal heat conduction equation. Unsteady resultant equation for the thermal conduction. Okay. Now let us see the, so now in order to make it more simpler, if in case my heat constant, that is K, if my K is remained constant, if the K is remained, assume that the K is equal to constant, in that case my equation will be simplified to dou rho E by dou T, equated to rho Q dot plus k into dou square T by dou square T by dou x square plus dou square T by dou y square plus dou square T by dou z square, where it have taken it as constant, where it has been taken it as k has been constant in that one, right? So in that case, my equation has been simplified to rho dou E by dou T is equal to rho Q dot plus and if I take one more assumption, that means the volumetric flow rate. One more assumption, if I make it that the volumetric flow rate of the heat transfer, if it is equal to 0, if my volumetric flow rate in that particular, if my volumetric flow rate in that particular fluid flow, so that if that is also equal to 0, then my equation would be simplified to dou E by dou T is equal to K into dou square T by dou x square plus dou square T by dou y square plus dou square T by dou z square. This is what my equation would be resulting when I'm considering that fluid flow has a net mass flow rate, that is volumetric change happening in that particular flow rate is equal to 0, when the volumetric flow rate is equal to 0. Right. So that is if there is no volumetric heat addition. If there is no volumetric heat addition, then Q dot is going to be 0 in that case. So then my resultant equation can be simplified to this one. So that is rho into dou E by dou T is equal to K into dou square T by dou square plus dou square T by dou y square plus dou square T by dou z square. Right. So dou square T by dou x square, y square and z square. So that is the equation I have brought it when you are going with and another one, there is no volumetric heat addition is being made in this particular fluid flow or in this particular problem. Now, so in order to address this one better, so let us go with this. In order to address this equation to the thermal conduction problem that is happening in between the two walls, how the heat is being transferred from one wall to the other wall. So just addressing that particular problem, So let me rewrite the equation here in this one. So that is rho dou E by dou T is equal to K into dou square T by dou x square plus dou square T by dou y square plus dou square T by dou z square. Okay, I've just rewritten that equation on just the top of the screen. I've just rewritten my equation. Now, according to the energy transfer from your thermodynamics, I can write the energy transfer happening in this particular fluid flow. I can write the energy transfer equation for this particular fluid flow as E is equal to CV into T. I can write that where E is the energy change which is happening in that particular fluid flow, but is by the conduction of this one. So if you are writing E, so this is nowhere I have made a magic from your thermodynamics. I have brought it that E is equal to CV into T. So where it is talking about the energy change. So from that equation, if I am taking that one, then my equation would be dou T by dou T. So that means this is indicating the time and this is the numerator is indicating the temperature. Dou T by dou T is equal to dou T by dou T. That is just substituted with a CV into T. So where CV is constant, that is the coefficient of volume, and rho, where I'm just sending it onto the other side, that can be becoming K by rho into CV, K into rho by CV. So can I write this complete equation as like, I can write the complete equation of dou square. So let me take some constant value of this one. So can I write it as dou square T by dou square T? Okay, let me write it as an expansion form only. Let me write into the expanded form only, dou square T by dou y square plus dou square T by dou z square. So let me write it in the expanded form. And here if you notice, so if I take any alpha coefficient, of this particular term and this particular differential format, if I write it, so can we write it as d square T by d. So where it is variation along the x, y and z direction, we are taking it. So that exactly is representing the variation of the temperature, where it is alpha is a diffusion coefficient, alpha is equal to K by rho into CV, and here if you see in this equation, these terms are varying parabolically. Every term in this one is varying along the parabolic in nature. That is the square times of it is being varied on this one. That is the square times of it is being varied on this one. So that is what it is, the beauty of this particular one. Mathematically, I'm approaching it to the unsteady thermal conduction problem. Unsteady thermal conduction problem, and the resultant equation has been brought up. The resultant equation has brought up completely into the one-dimensional diffusion equation. One-dimensional diffusion equation have brought it in this one. So that which we have stated in the earlier of this one, earlier studies of this one, we have stated it. So that is being resulted on the screen now. That has been resulted on screen now. Okay, if you're not sure where exactly we have done in the last one, so let me save this one and let us go back quickly onto this one, so that previously if you have seen. So initially, before discussing the problem, I told, so the nature, this form of equation is parabolic in nature. Before talking about the equations, we have discussed about the parabolic equations. We have discussed about this parabolic equations. Here, if you see, so that is similar format. So here is the current one. If you see the current one, if you see, so that is in the similar format of this equation, not this. Yeah, so not this. Yes, this one, because we have currently, so that is dou t by t is equal to alpha into dou square f by dou x square, alpha f by dou square by dou x square. So this is what we have. So dou t, so where is the function of temperature, and here it is a function of x square, here it is a function of x square. So that means f is actually t here in this one, and if it is varying only along the x-axis, so that is the format of the fluid flow. So that is the format of the fluid flow, where we have the resultant equation, So that is a diffusion equation. So if you are talking about the one-dimensional fluid flow, so that means where we are discussing with the diffusion equation can be said as one-dimensional fluid equation in diffusion terms. The one-dimensional fluid equation in the diffusion terms. So that is what about the resultant equation we have seen today about the parabolic in nature. So finally, this is a function of the term. So that is, this is a function of the temperature. So that is dou t by dou t is equal to alpha into dou t square by dou x square. If you are talking about only one dimension image, if you are talking only along the one direction, the change is happening. If you are talking about only along the one direction, if you are saying that it is only along the one direction, the change is happening. This is what the equation is being resulted in the parabolic equation. This is what the resultant equation, which is in the parabolic in nature. So that is what the conclusion of this particular session. The parabolic equation, the unsteady thermal conduction problem, has been addressed in this particular session. The finally the resultant equation, when it is in the one-dimensional variation, so that is going to be resultant on this one. That is going to be the resultant of this particular one. Let us see the mathematical variation. in the next one. Okay. So in a way, now we have obtained the governing equation for the heat problem which is happening in between the two walls. That is the wall 1 and wall 2, when the heat is being transferred, and here the in between medium is air. So the in between medium is air, and this is the temperature at the wall 1 and temperature at the wall 2. So where they are being separated by distance of length L, and this has been extended on both the sides. It has been extended. So this is the temperature of the wall 1, and this is the temperature of the wall 2. For this particular problem, now we have brought the governing equations. And this governing equation is stating that, so which we have discussed even earlier in the earlier sessions also, so that this is actually equation of the thermal diffusivity. This is actually very similar to the equation of thermal diffusivity. Okay, so this equation is very similar to the thermal diffusivity. So that is the thermal diffusivity equations are being similar to our, so that means they are actually parabolic governing equation. They are actually the parabolic equation for the fluid flow problem. So this is what earlier in the previous introduction sessions we have discussed about this one. So that is a thermal diffusivity problem. So now let us see what is the use of this particular governing equations we have obtained, and what exactly this is going to reveal us. By knowing this particular governing equation, so how it is going to help us, right? So let us move on to that part. So let me take this particular total equation. And now here our problem has remained same. So that is a heat transfer in between the two walls. So let me take it on the. Let me take this particular problem and go. Now if you see on the right hand side of the left hand side of the equation. So when one variable is varying with respect to the other variable, that if you see the x versus t here in this graph, if you see the x versus t, if you are here in this graph, if you see x versus t, so they are So the x versus t, they are how they are varying. So they are varying square times of the other one. So the one is varying other with the square times of it. The other is varying with respect to square times of it. So that this axis, let it be the x, and this let it be the, so let it be the time t. So let it be the time t. So here if I am writing it as time t, and here if I am writing it as x, and here if you see, so that means this particular problem of the thermal diffusivity is something which is stating that, so when you are plotting the value, so when you are plotting the value, so that is going to be some parabolic curve. This is going to be resultant in the parabolic curve. Now the question comes, how exactly this parabolic path is exactly, how the heat is being transferred. So actually we were talking about the heat transfer from one end of the wall to the other end of the wall. So that may be transferring directly from one point to the other point. So let me take the another color. So that may be directly transferring from the one point to the other point, or it may follow different parabolic paths in that particular flow criteria. So it may reach from a point 1 to the point 2. It may reach from the point 1 to, so that is wall 1 to wall 2 when it is reaching it to. So it may follow different trajectories that is dependent upon this thermal diffusivity equation. That is dependent on this particular thermal diffusivity equation. So that is how do we utilize this particular mathematical form of equations and state a physical problem, a mathematical utilization of this one, and how it is going to be resultant with our practical problems. So that is it. So if anyone is not clear how exactly I have written that E is equal to CV into dt, so they can refer to the proof of pressure. They can refer to the proof of pressure. So from that one only I have written. So where in this notations it has been given as U is equal to CV into dt. So where in our notations it is E is the energy transfer. E is the energy transfer, from that only I have written. So where E is equal to CV into T. So if anyone is not clear about that one, they can refer to that. Now here in this, let's see. Here in this one, you can see whatever the thermal diffusivity we have brought it. So is it similar to this particular problem what we are dealing exactly? Yes. So we are similar to this particular problem. So whatever we are dealing with this one, so that means this governing equations, that is the governing equation which is stating about this thermal diffusivity flow problem. So when you are T1 to T2, so that means how the heat transfer is happening in this particular fluid flow. So now let me annotate on this one only on this graph. So let me annotate on this graph and let me take some enlarged view of it. So let me take an enlarged view of it and let me annotate on that one. So now this is what actually the wall in between the two walls, how the heat transfer is happening by using the fluid conduction, by taking the fluid conduction. So here we have this is what how the x versus t is being plotted. So let me take an enlarged view on this one, and here in the enlarged view we can clearly see that the path of the fluid, the path of the heat, it is being transferring. So it may be transferring like this directly. So where t is, so that means what exactly this point is would like to state as. So if your time t, within a time t, your heat transfer is happening on this particular rod that is along the length of L. So how? So they are directly proportional. Your time versus length are being directly proportional. So that means within a few seconds, within the less time. So that means t is tending to where the heat transfer and the length both are proportional limits. When your heat transfer is more, so that means we can make more number of cases like sir, in some cases where the heat transfer would be very slow, although the solid materials in between the walls and the fluid is available. In that case, let us examine those all cases here in this one now. So let me take another case. Let me take the another case where the time consumption is going. So initially the gradual increase of the heat is being happening in between the time. So gradual transfer of the heat. So that means if you see for a less time, the more the heat is being transferred up, approximately more than the 50% of the length the heat has been transferred. But whereas at the time T2 if you see, case if you see, so at this instant only, so it has been transferred, not even 50% of the heat is being transferred at the T2 time. So when I'm following the second path, when I'm following the zero path, so there is no heat transfer happening. When I'm following the T1 path, yes, the heat transfer rate is high compared to this one. Okay. So this is what showing you about the parabolic variation of the flow, parabolic variations of the flow problem, how it is varying on that particular problem, flow problem. Okay. So that is what all about that parabolic heat transfer problem. So heat transfer problem, that is the unsteady thermal conduction problem we are dealing with. Unsteady thermal conduction problem. You can see how the heat is being transferred from one part to the other part. So different paths it can follow with respect to the time. So different paths it is following with respect to the time. So that is governed by our equation of the diffusion. That is governed by the equation of the diffusion. So that is what we have seen in the governing equation. So where with respect to the time, how the fluid flow problem is being varying, whether with respect to the time, how the fluid flow problem is varying with respect to that particular one. So how the heat is being transferred along the length L, So that means from this point to the other point, how the heat is being transferred in between this one by in conduction with the fluid problem. In conduction with the fluid problem, how the heat is being transferred. So that is being addressed here in this one. So this type of problems are generally parabolic in nature. This